aren't done yet. I will have them done by the next lecture, definitely. Probably you'll see the score on D12 before then. But so we're going to go ahead with the new section. We do have a lab this week. So for you guys, Monday or Wednesday, excuse me. And it's going to cover LEDs. So it's going to be something a little bit in the past. But it'll be fun. It should be a good lab to do just to kind of tie up things. And it's still relevant on the final. So you'll, even if you think you've stated enough, it'll help in the final. So let's go to the next step in this course. So we're going to cover something called intermolecular forces, which are, I mean, they get second string. I mean, you learn all about regular chemical bonds, covalent bonds, ionic bonds, because these are the strongest forces that keep atoms together. But intermolecular forces are just as important. They're much weaker connections between atoms and molecules. But they're super, super necessary in biology. So in proteins, in DNA, I mean, everything biological has to do with intermolecular forces. How we taste, how we smell, how all that works, all intermolecular forces. So we need to start by having a framework with which we can talk about things. Since a lot of this is going to be biological or organic, we need to talk about organic chemistry, organic compounds. And the way that these are classified is a little bit different from the compounds we've studied before. We previously had taken a look at binary inorganic compounds. Binary meaning just two parts, whether it's two elements or two pieces like polyatomic ion and a metal, something like that. And it's all been inorganic. And inorganic are compounds that do not contain carbon and hydrogen bonds. Okay? So organic is what we're going to be focusing on now. These are things that contain carbon-hydrogen bonds, along with other bonds as well. We could have plenty of other atoms, but the main part is that you need to have some kind of carbon-hydrogen connection. And it's got to be both carbon and hydrogen, not just carbon. So carbon and hydrogen. So now we know that carbon has 4 bonds. It's got a coordination number 4. You saw with diamond the possibility, and graphite, the possibility to make these really large structures. Well, it's not just with carbon. You can make these not very large, but you can make fairly large molecules with carbon, and you can make any kind of, honestly, any molecule you can think of, you can probably make it with carbon. So we're going to focus on pieces of organic molecules that make them that behave the way they do. So for instance, this is ethyl alcohol. This is the stuff you drink to get drunk. And what makes it an alcohol is the presence of this OH connected to a carbon. So this is a condensed structure. We did cover this before, but this is a condensed structure. This carbon is connected to that carbon. That carbon is connected to that oxygen. And then the hydrogens are just kind of like, well, they're also connected to the carbons. And this hydrogen is connected to this oxygen. So you need to be able to read these condensed structures and be okay with them. There it is. There's ethanol. Notice I said ethanol. It's another way to name them. We're going to go over a little bit of the naming, but not a whole lot. Ethyl alcohol, ethanol, grain alcohol. These are all the same names for the same thing. Soap is an example of an organic compound. There's a line drawing. And remember that in a line drawing, these are carbons. The end of a line is a carbon. That's a carbon. And when you see a line drawing, you have to remember that carbon should have 4 bonds. So if it doesn't show 4 bonds, then the other bonds that it needs are implied hydrogens. So that carbon at the end has only one other bond that you can see. So this carbon has 3 hydrogens on it as well. 3 hydrogens that are not shown, plus the 4th bond to the other carbon. And if it's not carbon and hydrogen, then you have to explicitly write it out. So this thing over here, C, with a double bond O, and an O here, with and then this is a little bit funny, but it should be a minus charge, and then a sodium with a plus charge. This is based off of an acid. but we'll cover that. Yeah, so dyes and drugs, all sorts of things are organic. Here's caffeine. We got a bunch of carbons, nitrogens in the blue, and oxygen in the red. White are hydrogens. These are just examples. That's it. So, would you classify? Oh, I forgot to click here. Sorry. Would you classify this compound as organic or inorganic? And I guess for this one we can just yell it out if we want.
Do you know the compounds?
Hold on, they were there. Wait a second. Did it work? Let's try it again. So this C8H18. Let's disappear again. Hold on. We're almost there. Hold on, it's not recognizing. Just give me a second. Alright. You guys know what you wanted to vote for, but it's it's not working there. There we go. Whatever you have in mind. No. There we go. This is it. There we go. Organic. So why is it organic? Because we have carbon-hydrogen bonds in it. Okay. C8H18 is a big carbon chain, usually 8 carbons and then 18 hydrogens. What about CaO? This one I can turn on. Oop, nope. There we go.
If it feels like it.
All right. So that one is very good. Everybody's seeing it as inorganic. No carbon, hydrogen, no carbon, no hydrogen at all. So it's got to be inorganic. This one, I'll just leave the clicker on. You can change your answer.
My kid's not turning off.
Mine too.
It's probably a battery. Oh, should be enough for both of you.
I do not know how to get this one off, but
Yeah, it's kind of broken. Okay. Yes, organic, definitely. I mean, you can see the carbon-hydrogen bonds here. Carbon-hydrogen. That one. Oop, I shouldn't have turned it off. Anyway. Okay. So we're doing this quicker. Inorganic, yes. And so there's plenty of these. So we're going to be skipping around a lot for this. So when you go to your Mastering Chemistry textbook, there's a lot of different chapters. So there's chapter 4, there's chapter 21. I think I've got it listed out, but you'll be able to pull this up again if you need to. So we're going to bounce around a little bit. So let's start off with the basics of basics of organic chemistry. These are the basic hydrocarbon types. And so again, we're using a different naming scheme because these are organic compounds, not inorganic. Inorganic covalent bonds, we would use the prefix and we would name the first thing first and the second element would have the IDE ending. That's not this. This is organic. There's a new naming scheme. So first you have to identify if your compound has any single bonds, or should I say any double bonds or any triple bonds. If it's only single bonds, it's an alkane. That's the class of compounds. It's an alkane. And that ane ending at the end is where you'll see see it. So ethane means there's only single bonds in this compound. F, by the way, means 2, which we're not going to go too much into, but F means 2. The ane ending means all single bonds. So 2 carbons, single bonds. An alkene has at least 1 double bond in it. It could have more than 1. There's a way to show that in the name. We're not going to worry about that. So there it is, alkene. And the This has actually a couple different names, even though the one listed here is ethylene. That's like the common one. The true, like, formulaic name is ethene, actually. So ethene. But ethylene, this is the stuff that ripening fruit gives off. So when you put a banana with other fruit in a brown paper bag, the banana will ripen, give off ethene, which will catalyze other fruit to ripen. So that's why you put it in a bag. Anyway, if it's got at least one triple bond, then it's automatically an alkyne. Why any? So this is technically ethyne, but the more common name is acetylene. So that's the stuff you burn with, some pure oxygen, and you'll get like a super hot flame for welding, things like that. And then there's a special case, which you are familiar with, because we've studied benzene before, where benzene has these double, single, these alternating double, single bonds. And in a Lewis structure, when we do a Lewis structure of benzene, we have to do resonance structures. So whenever you can do that with one of these organic compounds, it is now called an aromatic compound. And usually we're going to see this ring in there somewhere. That's
So what makes it aromatic?
the fact that it has these alternating double and single bonds that you can do resonance structures with. Most commonly, this benzene ring is what you'll see in aromatic compounds, but it's not the only one.
So it's a mix of double and single?
Yeah, so we wouldn't call this, so any time you have a double bond in a compound, it's going to be an ene, an alkene, unless that double bond is part of this kind of ring system where it's alternating single double, and then it's an aromatic compound, as we call it. Okay. Okay. So some more terms, and you've heard these before, maybe not in the context of chemistry though. Saturated compounds are compounds that contain only single bonds. And this is the same saturated that you hear in saturated fats. And so a saturated fat is a long chain hydrocarbon, like similar to the soap molecule I showed you before, but that particular fat has only single bonds in it. I think it used to be bad. I think it's not bad anymore. I forgot the current research. Saturated fats aren't so bad anymore. So alkene, alkyne, aromatic. These are all unsaturated. So as long as it contains a double or a triple or more than one of them, it is unsaturated. Okay.
So the first one is just saturated, the middle two are unsaturated, and the last is hydrogen.
All of these are unsaturated. So in terms of saturation, we're talking about the maximum number of hydrogens you can add to it.
So the only one is, and the last one is hydrocarbon and unsaturated?
Yes. Well, so they're all hydrocarbons. They're all hydrocarbons. This one is aromatic and unsaturated. Yeah. Okay. Let's look at kind of the characteristics of basic hydrocarbon. So these are alkanes, just single bonds. And if you take a molecule that has one carbon, methane, up to 5 carbons, pentane, so that's ethane, propane, butane, pentane, all those in between, it's all gas. And it has a boiling point of less than, most of them less than 0. Pentane is barely a liquid at room temperature. You can carry it around, but if you open it up, it just kind of vaporizes super quickly because its boiling point is 30 degrees, not very warm. And then look, as you add more carbons, the boiling point starts going up. So 5 to 12 carbons in a chain. This is what gasoline is composed of. Your boiling point goes up. When you add more carbons and you get to kerosene, diesel, you have a higher boiling point. And then even more carbons, you get lubricants. More carbons, you get paraffins, it's like candle wax. And then even more carbons, you get asphalt. And the boiling point just goes up and up and up. And so asphalt is just like tar, right? It's solid almost. It's so there's so many carbons. So there's something there. Why is the boiling point going up? What is it about the extra carbons? Is it just the weight, or is it something more than that? So here are the actual alkanes, 1 through 10. So notice the names, meth, the same meth that's methamphetamines. That meth part means 1. In the methamphetamines, it means there's a single carbon coming off of one somewhere on that molecule. Prop is 3 carbons, but is 4 carbons. And then when you get past 4, they start becoming recognizable: pentane, hex, hept, oct, non, dec. Those are, hopefully you've heard those prefixes before when it comes to numbering. But that is the organic naming system. So the first part tells you how many carbons there are. The second part tells you what class of compound it is. An ane ending is an alkane, single bonds. But I guess what to look at here is the boiling point. It just goes up as you add more carbons. So again, please get comfortable with the different Lewis structures and types of drawings. Here is butane as a plain old Lewis structure. Here it is as a condensed structure. These are both condensed, just different kinds. Here it is as a line structure, and there is a ball and stick model. So you should be able to see any one of these and be comfortable with understanding what you're seeing. Right? Now, the general formula of an alkane is however many carbons you have, you'll have 2n plus 2 hydrogens. So double the number of carbons, add 2, basically. So if I have 6 carbons, double 6 is 12, add 2 is 14. There's going to be 14 hydrogens. It's just a quick way to know if you're dealing with a plain alkane or not. If that formula fits this scheme right here, then you have an alkane. And if you don't know, remember this, you can always draw it out. Just draw it out, and then count the number of hydrogens. There's going to be 2 hydrogens for every carbon, except for the outer side, the left side and the right side, which will have an extra 2. The arrow's pointing the wrong one. That's okay. So, which one's the correct formula for a hydrocarbon, an alkane, that contains 8 carbon atoms? Is it working better with batteries? Yeah, okay, good. They should flash red at you, but I think people just ignore it until it just dies immediately anyway.
They did for a little bit, and then they just turn off.
Yeah. All right. So everybody thinks B, and I didn't see the answers, but yes, it is B. Excellent. So again, draw it out. If you don't remember the formula, it's fine. Just visualize what it should look like. Now, it does say non-cyclic because you can make cyclic compounds where the chain isn't a chain, but it's a loop. And then the number of hydrogens will change, but that's not the standard stuff we're going to be looking at. We're just looking at basic alkanes right now. So, let's draw a hexane real quick. Condensed structure, structural formula, and the line formula. Just to make sure. So hex, that means 6 carbons. And an ane ending is an alkane. So 6 carbons, an alkane, we're going to put them in a row like this. 1, 2, 3, 4, 5, 6. And every carbon needs 4 bonds. So tedious. So this is a structural formula. It shows you the structure using the correct number of atoms. A condensed one would be something like this, where you just kind of show the general outline of what it looks like. So the carbons are in a row. So we're going to do CH3, CH2, 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 and CH3. You could put bonds between them if you like, that's fine too. But that's a condensed formula. And a line formula, 1, 2, 3, 4, 5, 6. So every end, 1, and every bend, 2, 3, 4, 5, 6 is a carbon. That's hexane as the line drawn. The reason we do it zigzag is otherwise you wouldn't be able to see the bends. But, if you guys remember from 221, everything's tetrahedral. So they kind of do this zigzag pattern when they do these. If you ever build this, you'll see it. Okay. And we're not going to draw the ball and stick. That's something you build in a computer or with a kit, but that's what it looks like. So yeah, there you go. Tetrahedral. Naturally, it does this kind of zigzag shape. And it doesn't kind of loop on itself. It wants to be, we're going to learn that the carbons kind of want to be as far from each other as possible. Okay, so that they're not, like this, if you do a model, you'll be able to like rotate this and you can make this kind of structure loop back on itself a little bit. But it's not what it normally wants to do. It wants to look kind of like this.
I have a question.
Yeah.
Instead of like writing the condensed like that, can I just put like CH2 parentheses around it and like a 3?
Yeah, that's another good way to do it. So what she's saying is CH3, and then there's 1, 2, 3, 4 CH2 groups. So you can do this. It's a little bit harder to read, but that is a valid condensed structural formula too. Yeah, that's fine. Okay. The last one we didn't talk about was the space filling model. That's a lot harder to see structure with, or it should say, not structure, but the components. You can't really count atoms very easily. But the space filling model gives you an idea of the sizes and the space that everything takes up. Now, what is this slide all about? Well, it's about structural isomers. And this is this is not the bad part. This is like one of the features of organic chemistry is that there's so many ways you can combine, what is this, 4 carbons and 10 hydrogens. There's not so many, but there are a few. So these are all the same formula. They're both C4H10. You can count if you don't believe it, but they're connected differently. So here you have 4 carbons in a row. I should say here, you can see it better. Here you've got 3 carbons that make a chain, and the 4th carbon, instead of being on the end, it's on one of the middle carbons. So these are what are called structural isomers. So an isomer is anything that has the same formula, and you describe the kind of isomer it is with the first part. So this is a structural isomer, you just built differently. We'll look at other kinds of isomers later, but isomers generally always have the same formula. And so when we start getting into organic, it's no longer enough to kind of write a formula. C4H10 could mean a couple things. So we have to be more clear. We have to show either a condensed structural formula, or we'll have to name it properly. So notice these are named differently. This one's butane. This one is also a butane, but it's called isobutane. We're not going to get into the iso stuff. That's for organic, if you guys ever get to that class. But another name for this would be propane with a methyl group attached, so a meth 1 carbon. 2-methylpropane, it's called. Anyway, we're not going to get into the naming because that's too much for this class. We want you to be familiar with kind of the different structures you might see. That's pretty much it. So let's draw some isomers for hexane, just to be sure. Here's one of them. So I'm going to just do line drawings. So obviously, let's make some branches instead of making a long chain. So here's 1, 2, 3, 4, 5, and the 6th carbon we'll put here. There's another isomer of hexane. It's got 6 carbons, 1, 2, 3, 4, 5, 6. And if you actually draw the hydrogens out, there'll still be 14 hydrogens. Another one would be 1, 2, 3, 4, 5. There's the other carbon, is on the very middle carbon there. Do you guys see that? If I draw them out, maybe. So if I, or let's do the condensed structure. CH3, CH2, CH2, CH, excuse me, no, CH2, yeah. CH, CH3, CH3. So there's that one. This one is CH3, CH2, CH, CH3, CH2, CH3. Now, I'm going to draw one more. Well, I'm going to draw a couple more, but how about that one? So, is that one a different structure? So remember, these are 3D molecules, and to be a valid isomer, it has to be a different structure. It has to be connected differently. And this one is actually the exact same thing as this one. Because if I take this one and I rotate it, it's the exact same thing as this one in 3D, in space. So the idea here is, if I count the carbons from this side, 1, 2, 3, 4, 5, the branch is on the second carbon. If I count it from this side, 1, 2, 3, 4, 5, the branch is on the second carbon. They're exactly the same. So this is not a different isomer. This is the same as that one. This one is different because here the carbon is on the branch is on the second carbon. Here the branch is on the 1, 2, 3. 1, 2, 3. Whichever way I count, it's on the third carbon. But there's one more. What about two branches? 1, 2, 3, 4. How about that? 5, 6. And there's another one. 1, 2, 3, 4, 5, 6. Making sure everything has 4 bonds still. So if I draw CH3, 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 CH2, CH3. So everything still has 1, 2, 3, 4, 5, 6 carbons and 3, 5, 8, 11, 14 hydrogens, same. Let's try, I'll do one more. So what if you were like, okay, well, does the branch only have to have 1 carbon? What if we put 2 carbons in the branch? All right, well, if I did this and I did 4 carbons, and then I did 1, 2. Is that different? So this is tricky, and this is they're going to get you an organic on this. But if I count the carbons, 1, 2, 3, 4, 5. That's the longest chain, and I have a single carbon branched off of the third carbon. That's exactly the same as this one. So I have 1, 2, 3, 4, 5 carbons in a chain. The extra carbon is on the third carbon. It's exactly the same as that. It's just kind of the angles are different, but they're all tetrahedral. So even though I'm drawing it differently, it's all tetrahedral, all 1 and 9.5 degree angles. This is why organic can be hard for people. If you guys take organic in the next year, you need to be a lot more visual. You need a model kit. You need to build these things. But I just wanted to warn you that this is kind of coming up. So those are isomers, okay? Oh, and I meant to say this is same as that one. So just being able to recognize isomers, how to draw some isomers, that's it. I'm not gonna trap you here, trick you. And when you get to naming these funnier, non-standard chains, there are ways to name these too. So when you have a branch, you name the branch the same way you would name the main chain. You count the carbons in the branch. there's one carbon at the branch, it's got the meth prefix, 2 carbons, eth, 3 carbons, prop, 4 carbons, but, and it keeps going if you can. But instead of the A in the ending, the branch will have the YL ending. So you'll see something like methyl butane, something like that, you know. So that's means there's a butane chain, 4 carbons long, and there's a carbon branch on there somewhere. And then there's even funnier branches. So what if the branch is not a straight chain either? What if the branch has its own branches? So this is an isopropyl group. This is a T-butyl, terch-butyl group. So there's so many opportunities for naming in organic chemistry. All right? Again, I am not going to test you on what is the name of this thing, like something complicated. I want you to be able to recognize that what these, when you see a name, you'll be like, okay, this is a branch, this is something else. I can look it up if you need to, but it's not that necessary, okay? So yeah, there we go. This is 2-methylpropane. So propane, 1, 2, 3 carbons in the main chain. However you want to count it, you can count it this way if you want. But 3 carbons is propane, and the methyl branch is on the 2nd carbon of the main chain. So it's on the middle one. That's kind of what these names mean. So they're very methodical. It's and they get complicated. So again, you'll see this in organic. But we're going to be more focused on the kind of class of compounds you can make using other atoms besides carbon. So carbon is a useful, it's the structure, it's the backbone of all these compounds, but it's when you start adding oxygens and nitrogens that it makes it a lot more interesting. So whenever there is an OH attached to a carbon, just an OH by itself, that is an alcohol. I don't have a picture of it, but if you ever look at the structure of sugar, sucrose, it's a molecule that is a bunch of carbons in a ring, plus an oxygen in the ring too. But there's a ton of OHs sticking off of the rings of carbon. And so when somebody says, oh, it's a sugar alcohol, that's it's redundant. Sugars are alcohols. They just are more specialized ones, that's all. Because they have these OH groups on them. These NH2s make something an amine. You'll hear amino something, amino acids that are the building blocks of proteins. They're called amino acids because they have an amine group in them. They also have an acid group, which is down here. So we skipped alkene, but you guys seen alkenes. So in a carboxylic acid, whenever you have this pattern, a carbon with an OH, but not just an OH, it's got a C double bond O bond in there too. So when you see these things together, that is a carboxylic acid. Acetic acid, vinegar, that's vinegar right there. That's what's on the screen. There's 2 carbons. Because vinegar comes from what? It comes from ethanol. When you let alcohol oxidize further, you let the bacteria keep working on it. It will turn it into vinegar. And so you're taking the ethanol, which is this, and the bacteria slowly turns it into carboxylic acid. Citric acid, ascorbic acid, vitamin C, these are all carboxylic acids. These are all organic acids. So what if you took that H off of the O and replaced it with more carbons? This is what is known as an ester. Esters are fun because in food chemistry, this is where all of the nice smells and flavors come from. So a very common lab we do in organic chemistry is make something called isoamyl acetate, which is, it's a very simple reaction to do, but if you like Runts, the candy Runts, and if you like the banana flavor, that's the cell, that's the scent. It's the banana flavored Runts. Coincidentally, it's also a bee attack pheromone, so don't go anywhere near bees with it, but yeah, no, it's fun. And then amides. So an amide is something similar to an ester, but instead of the O with more carbons, there is a nitrogen, an amine group. which could have more carbons on it too. This gets complicated too. And amides are, if you're a fan of cooking again, when you do the Maillard reaction, where you brown meat or brown anything, you're making a bunch of amides. That's what makes it tasty. Not burning, but brown. All right, so we need to get comfortable seeing these functional groups in a molecule. So you'll have a big giant molecule and you'll have these pieces somewhere in it, and you'll be like, oh, there's this alcohol in here, there's this carboxylic acid here. These are pretty simple, but we'll see bigger ones. So, why do we care about these? Well, these create very, very specific properties for the molecule. So, if I take ethane, just 2 carbons, CH3, CH3, that stuff is a gas. But as soon as I put an OH on it, ethanol is a liquid, completely different properties. It'll make you drunk, ethane won't. But if I switch that OH with an amine, it stinks afterwards. It's really, really smelly. Amines are generally bad smelling. And then, of course, if I switch it to an acid, it's now vinegar. So they are all very, very drastically, these functional groups make drastic changes to the properties of your compounds. So we saw the previous slide that more carbons certainly changes the properties, makes things higher boiling point. But other things like this will also change the properties of your compound. Let's see. The only ones that you are going to be on the hook for are the ones that are blocked or rectangled out here. So alkane, alkene, alkyne, of course. We're going to focus on alcohols too. And yeah, these are all functional groups as well. You don't have to know these for any exams or anything like that, but they exist as well. And ether is the old school anesthetic. That's not used anymore. Not for a long, long time. Amines, those are very important in biology. So here's some more. An aldehyde. That's a new one. So this, you have this so you have this carbon-oxygen double bond. And what's key here is on one side you might have carbon, but on the other side has to be a plain hydrogen. That's the requirement to be an aldehyde. Probably the most famous aldehyde is formaldehyde, the stuff you preserve dead animals in. Formaldehyde, form is the old school name for meth, meaning 1 carbon. It comes from, it's kind of a creepy origin. Form comes from, I don't know the Latin name, but in French it's fourmi, like ants. And it's because you would get formic acid by crushing ants and distilling their dead bodies down. So that's where formic acid comes from, and you can turn formic acid into formaldehyde and other things. So that's where the old name comes from. Anyway, but aldehydes. Ketones. Ketones are, again, this carbon double bond O, but on both sides you have to have carbons. It's a requirement to be a ketone. Most famous ketone, acetone. Acetone is right there actually. Just 2 carbons on either side, that's it. So the formal name is propanone, but we know it as acetone. So notice that the formal names all have still the number of carbons in their beginning, prop meaning 3, and the ending kind of indicates the functional group. ONE, ketone. Al, ethanal, aldehyde. OL, alcohol, ethanol. So there's more. So carboxylic acid is ethanoic acid, that's vinegar, or acetic acid. We've got all these different names that have been in use for hundreds of years, and they're slowly switching to more formal names, but we still use those common names a lot. Okay. Again, here is the same. Oh, now it's actually got more on there. So I will say that this is the one that you should look at. This is the one that we're going to go with. And this has got more than before. But alcohols, ethers, aldehydes, ketones, carboxylic acid. So notice the carboxylic acid has the C double bond O, but it must have an OH on one side. An ester must have the C double bond O, but it must have an oxygen and then more carbon. So this R here, all these R's, is a generic carbon chain. Whether it's one carbon or two or three, that's what R stands for, is whatever number of carbons you want. But there must be carbon. Amines have nitrogen and some hydrogens or carbons. And it doesn't have to be the same either. It can be any number of carbons. So get used to these functional group names and be able to recognize what they are. So you will get this in a quiz and exam. Next week. So, let's look at these. What do we see here? Probably don't know the names very well yet, which is fine. But let's do the easy one. Here. What do we call this one? What kind of class of compound would I call it? An aromatic. Yeah, it's got that benzene ring in it. This is an aromatic hydrocarbon. What about this one? It's all carbon hydrogen. So the thing to look for is how many. It's not an alkane. If it was only single bonds, it'd be an alkane. The one triple bond means it's an alkyne. Yeah. All right, now the harder ones, non-carbon. So this thing, you have an OH in here, and the OH is connected to a carbon that has nothing else, just regular carbon hydrogen. That is an alcohol. And I don't see any others here. So this one, we have a C double bond O. We also have the C double bond O here. But you have to see what's connected to that carbon to know what kind of compound it is. So C double bond O with a hydrogen on one side only and carbons on the other side. That is what's known as an aldehyde. So that's an aldehyde. This one, a carbon with a double bonded O, and then carbon on one side, and O with more carbon. That is classic ester. That's an ester. And this one, which we actually haven't looked at yet at all, we did, but briefly. When you have an O surrounded by just carbon, no double bonds, no OH, this is an ether. So, make sure you go back. It was in this list, sorry. There it is, ether. So make sure you go through that list, get familiar with these compounds so you can identify these pretty quickly. Okay. So let's start, now that we have this kind of framework with which to talk about some of these compounds we're going to see, let's get to molecular forces. I'm going to start with a movie which didn't pull up on my other computer. Let's see if it works. Oh, it does work. Okay. I was getting errors. Use a better browser before. It was pretty bad. So we're going to look at kind of just what a solid, liquid, and a gas do at the atomic level. This is not a big.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature because the molecules of the solid have increasing kinetic energy. At the melting temperature.
Before we keep going, they're not mentioning something. Going back, this is a solid. You can see the atoms are kind of unmoving, but there's still all these green atoms that are flying around. And this is something we don't often think about, but even if something is a solid, even if it's at the temperature at which it should be a solid, every solid is still emitting a little bit of vapor. It's wild to think that that's really happening, but everything that is a solid is still emitting vapor. And the best proof I can give you is what happens when you leave your ice cube trays in your freezer for too long. The ice will just slowly disappear. And that's because the solid water is turning into a gas over a long period of time. So So every solid, at a different rate, but every solid will slowly emit gas particles, and that's where these gas particles are coming from, even though it's at a temperature where it should be a solid.
Increase with increasing temperature.
We'll talk about why.
Molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase.
So I think everybody understands that liquids will also emit gas. That's how water evaporates. You don't have to boil water to get it to turn into gas. It'll evaporate on its own. So liquids also emit gas particles. And that's why they're there, even though it's at liquid temperature.
At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy.
Okay. So that whole process, this is kind of a preview. We're going to understand every part of that process for this coming sections. But to start with, we need to understand what is holding those atoms or molecules together. And that is intermolecular forces. So these are the forces that exist between molecules in molecular liquids and some solids. So these are molecular solids we're going to be looking at. We're not looking at covalent networks. We're not looking at ionic compounds or metallic metals. We're going to be looking at molecular solids to start with, just to understand, well, how does a molecular solid become a solid to begin with? So CO2 molecules, yeah, there's a bond that holds the carbon and the oxygen together. Well, what holds two different CO2 molecules together in dry ice? So intermolecular forces do that. There must, this is the deduction. There must be some force holding it together, and that's, we're going to call these generically IMFs, intermolecular forces. So we understand a few ways why things might be might stay together. When we understand covalent bonding, we understand ionic bonding. And if we go back to Coulomb's law, which is what we used for ionic bonding, the force that holds two ions together is opposites attract. A positive ion is attracted to a negative ion. And the stronger the charges, the stronger the force that holds those ions together. So we're going to use a variant of that to kind of understand intermolecular forces, because really that's what is holding molecules together. It's not full charges. It's going to be a fraction of a charge that's holding these things together. So we're going to cover all of this. We're going to identify these intermolecular forces. We're going to there's going to be more than one, usually more than one type of intermolecular force that a molecule might have, and we're going to figure out which one is the dominant force, and then we're going to explain the boiling points and physical properties of various compounds using these intermolecular forces. So, I forgot. Let's start with the basics. And in Model 1, there's just a basic diagram of water molecules in a liquid and then water molecules in the gas phase. In Model 2, which is where we are going to really get into it, is a chart of boiling points for a series of alkanes, a series of ketones, and a series of alcohols. So that's kind of why we needed to understand a little bit of organic chemistry first. So let's go straight to the workbook, and I have to look up the number. Actually, I don't know the number. It's probably page 65 or 64, something like that. But 63, okay, even further back. So let's try questions 1 through 11 and make sure they make sense. Digest this information.
Which page did you say that?
63. Yeah.
Thank you. like every solid and liquid emitting like vapor, is that kind of how smell works? Like something smelling like something? 'Cause even though it's like
Definitely part of it. So some things you can smell very well, some things you can't. Some things will have such strong intermolecular forces that even if they release a gas particle here and there, it's going to be so rare that you'll never smell it. But yeah, sometimes, let me think how the scent would work. Sometimes the scent, usually the scent like in flowers or something, it's from a liquid, and the liquid is volatile, and it will slowly emit small amounts of gas until it's eventually evaporated away, and then the flowers dried up or something like that. But yeah, that's I mean, you can't smell it unless it's getting into your nose, you know. So if it's a solid, it has to somehow turn into a gas. Yeah. and aqueous means, aqueous means it has to be able to dissolve in water.
Oh, okay.
Which that's the key here. So it
Oh, right,
couldn't be a
'cause-
metal in that case.
Okay, right, yeah. Okay, that's right.
Yeah, I was tricked for a lot. So.
I don't know, I think it's 76 or something.
What?
So I'll take a 76.
Uh-huh.
All I'm trying to do is cover up these classes, just pass those little matters.
What grade was it?
I'm gonna go to med school. That's what you used to do with college. You had a better grades in your classes. And
Oh, you're right.
Harder classes. You know, it's really bad in med school. You fail a class.
Okay. Okay.
I know I'd get A's though. I'm just fine with passing.
Mm-hmm.
2 seconds. And then we'll talk about this stuff. I can't do it here. So, well, hold on, I'm still, this is taking forever. There we go. Done. Okay. So let's talk about the answers real quick. I think this is hopefully pretty clear. It's this one is after evaporation. And 1B is a gentle reminder that these are physical changes. When you do a physical change, you do not change the particles themselves. So H2O is still H2O. You're not breaking any bonds. So on average, are the intermolecular forces stronger in H2O liquid or H2O gas? I do not like this question because they imply, and they actually say so, that the attractive forces are stronger in the liquid than the gas because the molecules are very close to one another. Yes, the closer something is, according to Coulomb's law, the more attraction there is. That's true. But there's no difference between liquid and gas in terms of how attracted they could be. Meaning, yeah, they're not very attracted because they're far apart. But if I were to somehow take this gas molecule and put it real close to it, it would have the same attractive forces as liquid would. It's just, what's different is that the gas molecules have a lot more kinetic energy. They're moving a lot faster. And that's what keeps them apart, okay? I think it's a very confusing question. So, the forces that keep water as a liquid are the same as if they were in a gas, but it's just since the molecules are further apart, they're just not feeling that attraction, and so they stay in the gas. Okay. So now we come to this, where we're comparing different formulas, different kinds of organic compounds. Let's go straight to the questions. So individually, probe the Lewis structure for one propanol and then predict which bond will be the shortest and what the COH bond angle will be. So one propanol, which is right there. Which bond is the shortest? So if you had to draw this out, or let's do condensed. And then I kind of highlighted the bonds that really matter here. Which one of these is the shortest bond? The OH. Remember, we're talking short bonds you get from small atoms. So hydrogen is, yeah, the smallest atom here, but is a hydrogen carbon or a hydrogen oxygen bond shorter? Compare oxygen to carbon. Oxygen is smaller. As you go to the right of the periodic table, the atoms get smaller. So this bond is the shortest bond because it's made between the smallest two atoms. Okay. Oh, and then what are the bond angles here? So if I look at any of the, like this carbon, oxygen, hydrogen angle, what should the bond angle be? So this is where Lewis structures come in. You have to remember that even though these are not Lewis structures, these organic drawings, yeah.
Should it be linear?
No.
No.
Good guess there. So this is not a formal Lewis structure. These structural formulas are not Lewis structures, and that's because they do not show lone pairs. Oxygen here has to have an octet, just like carbon does. Oxygen likes two bonds. Well, why only two? Because what you don't see is that there is a pair of lone pairs on these oxygens. And so there are 1, 2, 3, 4 groups of electrons around that oxygen. This oxygen is tetrahedral electron geometry. But if you just look at the atoms, it's a bent shape. But that tetrahedral electron geometry means that all of the bond angles here are approximately 109 degrees, 109.5. It's not going to be exactly 109. It's going to be probably smaller than that because lone pairs make things bond angles smaller, but it's based off of tetrahedral. So these are all tetrahedral bond angles. Okay. So these structures we're doing, they're not formal Lewis structures because they don't show lone pairs. We just kind of leave them out. Too much trouble to draw that all. So recall that the electronegativity of carbon and hydrogen are roughly the same. So 2.1 for hydrogen, 2.5 or so for carbon. They're different, but they're in chemistry we think they're close enough to be relatively similar. And so they're going to make nonpolar bonds. Carbon-hydrogen is a nonpolar bond, according to most chemists, okay? But once we introduce oxygen, which has a higher electronegativity, what's going to happen to your compound? It's going to go from nonpolar to polar now. So alkane is going to be nonpolar because it's just carbon-hydrogen bonds. But a ketone, or an alcohol, which has an oxygen in it, which is very electronegative, is going to make that a polar molecule. But let's kind of take a look at how the boiling point changes between alkane, ketones, and alcohols.
Sorry, for ketone and alcohol, it's non-polar. I mean, it's polar.
Polar, yes. So to compare 3 of these, we should compare similar molecular weights, just so that we can rule out any other factors, right? So we want to keep everything the same. We just want to look at, well, what's the difference between an alkane, a ketone, and an alcohol? So if you look, there is, let's see, and they're not going to be perfect, but you know, this is 69, that's about 79, and this has a molecular weight of 97 or so. I'm sorry, I'm looking at the wrong, 74, I'm looking at the wrong number here, 74. Oh, I looked at the wrong number, sorry, 72. 72, 74. So these 3, pentane, 2-butanone, and 1-butanol, have approximately the same molecular weight. Approximately. So we can rule out any molecular weight issues. And now let's look at the boiling points. So this one is 36 degrees. That one's 79, 80 degrees. This is 117 degrees. So alkanes, if everything else is the same, has a much lower boiling point. Ketones have a mid-level boiling point. Alcohols have a really high boiling point compared to the rest. So far, so good? Okay. So what does that mean about intermolecular forces? How does the intermolecular forces between the molecules change as the molecular weight increases? Well, we look at each one of these as its own category, right? So for alkanes, as you increase the molecular weight, the boiling point increases. As you increase the molecular weight of ketones, the boiling point increases. as you increase the molecular weight of alcohols, right here, the boiling point increases. So, if boiling point is related to the intermolecular forces, which it is, then as your molecular weight increases, your intermolecular forces increase. Okay? So we've got two factors. Actually, I guess I did 7 already. Find an alkane, ketone, and alcohol with roughly the same molecular weight. Rank these compounds. All right, I did those already. Sorry about that. So repeat question 7 with 2 more sets. All right, I guess we can skip that one, maybe. But let's, 86, 86, and 88. Those are practically the same, and it's the same pattern still. 69 low, 102 mid-level, 137 higher. Still the same pattern. The alcohols have the higher molecular, higher boiling point. So, using grammatically correct sentence, describe any general pattern you can identify about the boiling points of alkanes, ketones, and alcohols. The alcohols have higher boiling points. Ketones, not quite so high. The alkanes are going to have the lowest boiling points. 9, rank the 3 types of compounds in terms of their relative strength of intermolecular attraction. So this is the same thing. We're now, instead of saying it's the boiling point, it's the intermolecular forces. The higher the boiling point, the stronger the intermolecular forces that are keeping those molecules together in a liquid phase. If they're weak, then they're going to be able to turn into a gas very easily. You don't need a high boiling point. But if the connections, the attractions between those molecules are really strong, then you'll need a high boiling point. It's going to take a lot of energy to boil it, to break those connections and turn it into a gas. So alcohols have much higher intermolecular forces. Ketones are high, but not quite as high as alcohols. And alkanes have weak intermolecular forces. And so, does the presence of a dipole moment in a molecule tend to increase or decrease the strength of intermolecular interactions? Yeah?
Did you say, you said ketones have a low intermolecular?
Like mid-level intermolecular.
And the alcohols have?
Alcohols are the highest out of these 3 groups. So, is the strength of the intermolecular forces, well, no, I skipped 10. Does the presence of a dipole moment in a molecule tend to increase or decrease the strength? So, if I look at butane, right, this is butane, and yeah, there's a bunch of hydrogens, and there's a bunch of carbons, but every single bond here is technically nonpolar. So there is no dipole moment in this molecule. It's a pretty nonpolar molecule. If I compare that to ethanol, or let's do butanol, I guess. I'll draw these out. So you've got this on the end, and here I'm showing the bent shape. This is a better description. There's a dipole moment here. All right, this is a polar bond. Remember how we do polar dipoles? So we show the dipole moment for the bond. We draw an arrow towards the more electronegative atom. And the same thing happens here. And we add up all the dipole moments. So notice that these are all pointing downwards. So the overall dipole moment is that way. This molecule has a dipole moment in it. A ketone, which, let me get an actual one that's from the chart. 2-butanone, why not? All right, 2-butanone. So CH3, CH2. Yeah, okay. So this one has fewer dipole moments. It's you know, there is a dipole moment here, but that's it. So there's a dipole moment in this molecule as well. And the fact that there's a dipole moment means it's going to have stronger intermolecular forces. Okay? Alkanes do not, so it has a low boiling point. weak intermolecular forces.
So dipole moments make it an increase in strength.
Increases the amount, the intermolecular force strength, yes. Is the strength of IMFs determined by the bond strengths within the individual molecules? No, it has nothing to do with these bonds that are inside the molecule, because we're not doing anything to these molecules. When we turn them into a solid versus a liquid versus a gas, they are staying whole. Nothing's happening. What's different is the attraction between two different molecules. You have a question?
Yeah, just because they seem so related, the type of bond and the force.
So within the molecule, yeah, these bonds will, so the bonds inside the molecule will give the molecule as a whole certain properties. So the fact that there's a dipole moment here, the fact that there's a dipole moment from these bonds, that dipole moment itself is what causes the molecules to interact with other molecules in a certain way. So, I mean, when we talk about is the bond strength involved, we're talking, well, a bond strength means, well, how much energy does it take to break the bond? We don't need to break any bonds. So the bond strength has nothing to do with it. The bonds do, but not the bond strength. Put it that way. Okay. So, we're getting a clue into what's going on. So see these dipole moments, these polar bonds, these polar molecules are somehow increasing the intermolecular forces. So, if we already answered this one, water evaporates, the bonds between hydrogen and oxygen atoms are broken, false. And for a series of molecules, the molecular weight of the as the molecular weight increases, the boiling point increases. And as far as these three categories of compounds, in terms of strongest to weakest IMFs, or weakest to strongest, I should say, it goes C, alkanes weakest, ketones next, and then alcohols the strongest. So the presence of a dipole moment in the molecule tends to increase the strength of the intermolecular attractions. Okay, so let's kind of dive into that a little bit. And so what you're looking at here is a graph that shows some unique compounds. These are all nonmetals with hydrogen, however many hydrogens they need to make a simple molecule. So this blue line, this is the group 6A elements with hydrogen, H2 tellurium, H2 selenium, H2S, H2O. And then here's group 7 with enough hydrogens, usually 1. Here's group 5 with enough hydrogens, 3. Group 4 elements with enough hydrogens. So like this would be tin with hydrogen. This is germanium with hydrogen. This is silicon with hydrogen. Anyway, that's what this is. And I think this part, by now, should be pretty much, you get it. Because what's happening here is we're going to compounds that have a higher molecular weight. And as you increase the molecular weight, we saw it in the other charts, the intermolecular forces somehow got stronger. The boiling points went up. And that's what's happening here. The boiling points of these compounds, as you get to heavier elements, is increasing. Now, what we still can't explain is, well, what's happening here? That's a little bit weird, because if oxygen with hydrogen were to fit in this chart, we would expect it to be somewhere down here, slowly going up. But oxygen, H2O, is way up here. CH4 fits, right? It's lower, and as you replace the carbon with silicon and then germanium, the boiling point goes up. So let's kind of dive into this. Well, we'll eventually get to it. So what are IMFs? What are intermolecular forces? So first, let's grammar-wise, let's understand the difference between intra and inter. An intramolecular force is a bond. Intra meaning within the molecule. So This is an intramolecular force. This is within this molecule, a force holding the two atoms together. An intermolecular force is what we're talking about, is a force between two different molecules. So there are some kinds of forces that are keeping, for instance, HCl molecules together. And so intramolecular forces, these are bonding forces, are pretty strong. So ionic covalent bonds, even metallic bonds, but the ionic covalent ones are really, really high energy. It takes a lot of energy to break those attractions. So to break an HCl bond, to break an NaCl bond, it can be anywhere from 100 to 1,000 kilojoules per mole. That's a lot of energy to break a bond. An intermolecular force is much weaker. So these are forces that act between two different molecules. These things influence the physical properties of molecules. They are weaker than covalent bonds, so notice the energy. So an actual covalent or ionic bond takes a lot of energy to break, but if you are breaking the force between two different water molecules, two different HCl's, like this force holding those two molecules together, you don't need to put much energy into it. It could be very, very little sometimes, to somewhat significant, but still pretty weak. So 40 kilojoules per mole is not nothing, but it's still a lot weaker than a regular bond. So these are the forces, these are the names of the different forces we're going to see. Ion dipole, dipole dipole, London dispersion forces, hydrogen bonding. And so ionic bonding, even though we've been calling it a bond, is technically INF. Because when you talk about what is the strongest part, what is the smallest particle in an ionic compound, what is it? It's the ion. So the cation and the anion in an ionic compound, there are actually two different particles. So technically, an ionic bond kind of falls into the category of an intermolecular force, right? You don't make molecules with ions, right? So that's why this is here. But it's a little bit of a gray area. It really belongs with intramolecular because the force that holds these together is so strong. So, the intermolecular forces, we've got a lot of names for them. And you saw the names on the previous slide. We can categorize them in different ways. So we're going to focus a lot on the van der Waals type forces, which includes dipole-dipole and London dispersion forces, which we'll get to. There is a special kind of intermolecular force called hydrogen bonding. We'll get to that as well. But again, they're pretty low energy, so van der Waals are pretty weak. Hydrogen bonding is stronger, but still kind of weak compared to ionic and covalent bonding, okay? And it ranges. It just really depends on what compound you're looking at, but those are the general ranges. So, the three main intermolecular forces we're going to look at are these three. And there's also ion, dipole, there's variations of these, but we'll get to them all. London forces, these are the weakest. London dispersion forces, another, sometimes it's called, add that word in there. These are the weakest types of intermolecular force. Every molecule does London forces. Everything does. But it's so weak that if there is a stronger force that is more dominant, then we're going to focus on that. So the other kind of force that could be a little bit more dominant is a dipole-dipole force. So these are attractions between molecules that actually have dipoles, like this one, like this one. This ketone will do dipole-dipole forces with other molecules of the same kind. This alcohol will do, well, this is a special case. We'll get to that in a second. And the last one is a hydrogen bonding. And it's a special case. It seems like it's the same as dipole-dipole forces. And it kind of is, but there's a criteria that needs to be satisfied, and once and we'll go over that. It involves hydrogen and nitrogen and oxygen and fluorine. And for some reason, the forces that you get from these dipoles that these elements make are stronger than normal. And so they have their own category. It's called hydrogen bonding. We'll get to that. These are the strongest. So, according to what we just looked at, alkanes, those only do dispersion forces. They only do London forces. They don't have any dipoles, so they have weak IMFs, and we saw that with the boiling points. The ketones only do dipole-dipole forces, which is fine. That's pretty strong, and that's why you have a higher boiling point. This alcohol will do something special called hydrogen bonding. So the OH does a special kind of intermolecular force called hydrogen bonding, and I'll show you what that looks like. And it's the strongest IMF, and that's why it has the highest boiling point. Water, by the way, does hydrogen bonding, which is why water is a liquid at room temperature for being such a light molecule. All right, here's another kind of comparison of the forces. Here's the bonding forces we've seen already. Ionic, covalent, and metallic. Metallic are the weakest, right? We've learned that. But they're still pretty strong. Covalent bonds, ionic bonds. There we go. But what about something weaker? So IMFs, where do those fit in? So here is a variation of dipole IMFs. This is called an ion dipole force, which is pretty strong, because what happens is you've got ions present, which have full minus charges or full positive charges. So like NaCl dissolved in water, for instance, or NaCl dissolved in a ketone or something like that. You've got these ions floating around, and you've got molecules that have dipole moments. And so we're not showing you the molecule, we're just showing you what the dipole moment looks like. So what is this about? Well, remember, a molecule that has a dipole moment, it has a partial negative side to it, and it's got a partial positive side to it. That's what these symbols mean. This is lowercase delta, it means partial. So it's not a full minus charge, it's not a full positive charge, it's a fraction. Doesn't matter what it is, it's going to be some fraction. It could be a large fraction, it could be a very tiny fraction, but it's some fraction. And these dipoles are attracted to the ions. The negative side of the dipole moment will be attracted to a cation. The positive side of the same dipole moment will be attracted to a negative ion, an anion. So these are fairly strong intermolecular forces. Because if you think about Coulomb's law, Q1 is going to be a pretty large charge. It's going to be a +1 or -1 or even +2, -2, depends on what the ions are. Q2 will be, or this is backwards, I guess. Q2 is the charge of the ion. So Q1 is going to be some fraction of a charge, so not very strong, but you'll still get a pretty good number from Coulomb's law that tells you how strong that force of attraction is. So this is exactly how salts dissolve in water, for instance. So NaCl is your solid salt, and these ions love to be near each other because they are attracted to each other. Their Coulomb's law says there is a strong attraction between two oppositely charged ions. So why then would a salt want to dissolve in water? Well, that's because the dipole moment of water has a positive side and a negative side, will do those same interactions. The positive side of water is attracted to the anions, and the negative side of water is attracted to the cations. And even though this might not be as strong as an attraction as an ionic bond would be, the fact that the salt will dissolve and will do this means that this is a favorable thing. Like there is pretty strong attraction between ions and water. Okay. Okay. So we need to start thinking of molecules in terms of the dipole moments. This is where 221, at the end of 221, we kind of did dipole moments, and hopefully you guys remember all that. If not, feel free to come by office hours, we can go over that stuff. But which one of these represents a solid? So here you have a molecule, but instead of showing you what the molecule is, we're showing you its representation as an electrostatic potential, where The red side is where you have a large number of electron density. The blue side is where you have a weaker, a smaller amount of electron density. And so the red side is going to have a partial negative charge. The blue side is going to have a partial positive charge. And if you were to put a whole series of these molecules together, and they were to make a solid, you would most likely have A, okay? Solids tend to be crystalline. Not always, but usually. When they do get crystalline, they will orient themselves where the positive side is as close to the negative side as possible, and everything is fairly well ordered. It's, it's repeatable. B is more likely a liquid. So in a liquid, the intermolecular forces are still in play. Positive is attracted to negative. But the arrangement is not so fixed. There's no pattern. They're just kind of moving around. So let's go back now to the dipole-dipole force. This is the standard IMF force that we're going to study. So no ions involved. Just let's talk about a pure substance here. Whenever you have a molecule that has a dipole, like this one right here, it can it can be attracted to other versions of the same molecule. And they will orient themselves in a way that maximize attraction. So another one of these molecules comes along, the carbon side will be pointed towards the oxygen. You're not going to have two oxygens butting heads. All right, they're both partially negative. They repel each other. Okay. And the more polar this bond is, and we don't really measure that. We can calculate it. Or we didn't actually measure it in 221, but we did a computer simulation where we calculated polarity. The more polar it is, the stronger the IMFs are going to be. So how do we judge how polar something is? For us, we kind of look at the difference in electronegativity, kind of look at kind of the structure. So sometimes you can have polar bonds, but it'll be non-polar overall, things like that. So just some examples. Carbon monoxide, chloromethane, sulfur dioxide, these are all polar molecules. And so these will do dipole-dipole interactions. So CO will interact with other CO molecules. It's the gas at room temperature, but theoretically, if you cooled it down enough, you could turn it into a liquid with maybe some pressure as well. And it will turn into a liquid or a solid even because it has a dipole moment, and the carbon partial positive side will be attracted to the oxygen of another CO molecule, and it'll make solids like that. You might need to cool it down really, really low, but you can definitely make solids out of it. And the rest of them will do the same thing. The stronger the polarity, the stronger the IMFs. The higher the polarity, the higher the IMFs. Ammonia is NH3, okay? NH3, and it's a gas normally. But when you think about household ammonia, the cleaner, it's always a liquid. Well, that's because the ammonia gas has been dissolved in water. And it should be fairly easy to see why ammonia and water mix together so well. Ammonia is a very polar molecule. It has a partial negative side. It's trigonal pyramidal. And so the oxygen side is partially negative. The hydrogen side is partially positive. It has a dipole moment. Water has a dipole moment as well. And so these will interact with each other really well. The partial positive side of one molecule will interact with the partial negative side of another. Here is a chart that kind of shows you similar molecular weight molecules, but we're changing the functional group to a more polar functional group as we go up in this column here. So you can see here dipole moment. This is how we measure dipole moment. It's something called the Debye. That's the unit we use for it. So this is just the strength of the dipole moment. And here on the vertical axis is the boiling point. So as you increase the dipole moment, the boiling point goes up. And we're trying to keep the molecular weights the same so that the molecular weight is not the, not the variable that's changing everything. So acetonitrile. This thing looks like this, just in case you're curious. So that's what acetonitrile looks like. This thing is really polar. And so out of all of these, it's the most polar, and it'll make a higher boiling point molecule than the others. This is a really funny one though. There's a ring, tiny ring with oxygen and 2 carbons. Anyway, don't worry about it. You'll go over this more in detail in organic chemistry. I don't know. Another thing you can see from here is the computed electrostatic potential. So the more reddish and more bluish you have the two sides, partial negative, partial positive, the more polar it is. So here you can see you go from not very much red, the red starts getting more and more dense, although it's harder to see here. Anyway, more polar. So, if I compare the group 5 hydrides, their boiling points would be what compared to group 4 hydrides? This is a tricky one, actually. We're talking about polarity, right? So what's the difference in polarity between these two groups? Take the first one of each group if you need to.
Group 5 would have a higher polarity.
Yeah. So, based on the fact that group 5 would make all trigonal pyramidal shapes, which can be polar. These molecules can be polar. Group 4 hydrides like methane will make tetrahedral shapes, which are completely symmetrical. They're going to be nonpolar. Because the group 5 shapes are the way they are, and they tend to be more, they'll make more polar bonds. And so you will have a higher boiling point for something like ammonia, or something like NH3, than for CH4. All right, so this is polar, and this is nonpolar. Okay. I am not a fan of this explanation, but it also makes sense too. I think the shape is the better explanation. But another reason is that the difference in electronegativity for group 5 hydrides is greater. So carbon versus hydrogen has a small difference in electronegativity, so it's fairly nonpolar bonds to begin with. Nitrogen versus hydrogen is a bigger difference, so it's a more polar bond. But I think the shape plays a better role in this case. So, make sure you keep looking at those tables of electronegativities. They are critical for everything, yes?
On the last question, I had thought of it as how many valence electrons they had. Is that, I still got the right answer, but was that just like...
Well, the number of valence electrons will tell you a little bit how many bonds it can make, but I don't know directly if there's anything about the valence electrons you can say. I mean, coincidentally, the more valence electrons you have, the more electronegative it's going to be.
Yeah, I was thinking even more polar, likely.
Yeah, okay, that's fair. That works too. But yeah, we're going to use electronegativity a lot. In organic chemistry, you'll use electronegativity a lot too, so this is never going to go away. You'll just have to remember some of this stuff. So here's that chart for the group 4 and group 5. And you can see that, yeah, group 5 is higher boiling point in general. And this part here, it's because of molecular weight. As you increase the molecular weight, we've seen that the boiling point also goes up. Again, this part doesn't make any sense. It should be down like this, but let's talk about why that is later. So, we want to do this. Hold on a second. Let's come back to this, but let me keep going with the slides. We're going to come back to this and do it maybe one Wednesday. What about nonpolar molecules? So I think we understand maybe how a dipole-dipole attraction works. They have this partial positive, partial negative sides of the molecule, and just like magnets stick together, north to south attracts. Two molecules will stick together a little bit from their dipole moments. So what if you have no dipole moment? Like this alkane. How does it stick together to another alkane? How does it make a liquid? How does it make a solid? And so this is what the electrostatic potential looks like. Pretty boring. It's like pretty even distribution of electrons everywhere. There is no partial negative side. There's no partial positive side. Well, so what are London dispersion forces then? This is a little bit tricky. So electrons, so we're not thinking quantum mechanics anymore. Let's think of electrons as actual things again. Actual little particles. Or think of them as things just moving so fast you can't tell where they are exactly. There's somewhere in that cloud. And it turns out that this cloud, where you can find an electron, is squishy. It's moldable. It's distortable. We can actually change the shape of the cloud. It can be influenced. Like you can actually cause this cloud of electrons to shift, to move. So going back to this, yeah, this cloud of electrons, or this is actually electrostatic potential, but you can think of it as a cloud of where you might find the electrons. It looks pretty even, but we can distort it. And that's where London dispersion forces come in. So if we can push the cloud to one side of the molecule temporarily, then the side of the molecule that has more electron density will temporarily get a partial negative charge. And the side of the molecule that gets squished, that has less electron density, will have a temporary partial positive charge. That's what's called an instantaneous dipole moment. It's a dipole moment that it exists for a fraction of a second as you distort the electron cloud, and then it'll go back to normal. But that instantaneous dipole moment is enough to attract or cause instantaneous dipole moment in neighbors and cause very weak attractions with the neighbors. So the fact that electron clouds can be distorted, squished, moved around, this is a property of a molecule called polarizability, or of an atom, I should say, called polarizability. Some atoms are more polarizable than others, meaning some atoms, some molecules can have their electron clouds distorted more easily. And I think if you think about it, you understand which ones would. So let's go over the force real quick. The London dispersion force, here's two helium atoms, completely neutral. And they have this 1s cloud of 1s orbital where the two electrons are. And they're neutral, so you wouldn't expect any interaction between them. But if if one helium atom comes flying at the other, it depends on which way it happens, but maybe the electrons are temporarily on this side of the helium atom, make a temporary, like instantaneous partial negative charge on one side of the helium, just for a fraction of a second. Well, that fraction of a second is enough for these electrons to cause the electrons in this helium atom to repel, to move away from it on this side, generating its own partial negative, partial positive, temporary dipole moment. And that's what happens here. You have this very, very brief temporary dipole moment, and that causes a temporary attraction. And it's super weak. It is weak, but it exists. It's there. And that's what allows things that are nonpolar to become liquids, to become solids. We looked at asphalt, which is a super long carbon-hydrogen molecule. There's no polar bonds in that, none. It's just CH and CC bonds. Yet, at room temperature, it's a solid. So these London dispersion forces, as weak as they are strong enough to make things solid at room temperature. Okay. It happens everywhere. Everything has London dispersion forces because as long as it has electrons, you can distort them. Some are easier to distort than others, but everything will do this. So I actually don't know what this question is. So, okay. So it's not a question. So in A, you have two completely neutral molecules. Maybe H2, maybe Cl2, something. Two atoms stuck together in a covalent bond, and these two molecules are coming closer together. There's no attractive force between them because they're completely nonpolar. But as soon as they come near each other, one may, and this is kind of random, okay, this is all probability based, one molecule may, like the electrons in one molecule, might cause the electrons in the other molecule to temporarily move away and create a temporary dipole moment where you'll get a brief attraction between those two molecules. And if you imagine this in a giant container, which is not a giant container, a regular container which has 10 to the 23 different molecules in it, this phenomenon is happening a lot, statistically. And that phenomenon is enough to make things liquid. I2, iodine, is a crystal. It's a solid at room temperature. Bromine is a liquid at room temperature. Chlorine is not, but you could cool it down and make it a liquid if you want. So these all things are nonpolar, yet they do strong enough IMFs through London dispersion forces to turn into liquids or solids. So yeah, this is kind of what is happening. You get all these chaotic interactions between different molecules, inducing dipole moments in neighbors, and then stopping, and then happening to it. You know, just so many different interactions that you get all these different inducing of dipole moments. But again, energy-wise, it's very, very small attraction. So to break apart the attraction from these induced dipole moments, from these London dispersion forces, it's about 0.1 joules per mole. Joules compared to the 100 to 1,000 kilojoules per mole. So we're talking seven orders of magnitude smaller than bonds. Okay, so it's super weak. 10 million times smaller. Now, where does mass come in? So molecular weight somehow causes boiling points to increase. Well, it's not actually the mass, it's a coincidence. It's kind of a correlation, not causation. It actually happens to be the fact that you have a greater mass, you tend to have more electrons. The more mass there is, the more atoms there are, the higher the, like, so let's say you do iodine versus fluorine. Iodine is a much higher molecular weight, but what else does iodine have? A lot more electrons. The greater your mass, the more electrons you're going to have. And the more electrons you have, the more likely you can cause distortions in the electron cloud. So we're going to get into this, and I want to stop here, but as you increase the molar mass, the boiling point is going to increase. And it has everything to do with numbers of electrons. The more electrons you have, the more possible London dispersion forces you can do, and the higher the intermolecular forces, higher the boiling point. There's more to it. We're gonna get to shape of the molecule, we're gonna get into other things, but hopefully we've started you off. So we still need to talk about hydrogen bonding too. We have to talk more about London dispersion forces, but we'll get through the IMS. Any questions on this so far? All right. Let's stop here. All right.